Okay. We going? Okay. All right. First of all, before we get back to finishing up this hydrocarbon series, I want to state for the record that the beta pinene isomer is just a change in the position of this double bond. So, not a change of a position of the methyl group. That would be beta pinene. But you do not have that in your kit, so. Pretty much you see this everywhere you see alpha pinene. They kind of occur in pairs.
If you bring a sample, can you see the difference?
I could bring a sample beta pinene in. It's not a huge difference, but there is a definite difference. All right, so we're still in hydrocarbons, covered alkanes, covered alkenes, and now we did the subclass of terpenes, and a monoterpene is built up of 2 isoprene units. So now I wanted to talk about sesquiterpenes. Oh, I should have said too. So in other words, the formula for monoterpenes, obviously, since it's built up of 2C5H8, the formula will always be C10H16. Always. To be a monoterpene, it has to have that formula, C10H16. And from monoterpenes is where most of your other types of components come from, your other oxygenated monoterpenes and sesquiterpenes as well. So a sesquiterpene consists of 3 isoprene units. So the formula for all sesquiterpenes would be what? Yeah, C15H24. So obviously these are heavier. Let me start back up here. Well, heavier molecules. Going to be less volatile than a monoterpene because of the larger size. Still, hydrocarbons still very nonpolar. And the example that you have for a sesquiterpene is the most common sesquiterpene in essential oils. It's called beta-caryophyllene, and the structure's there in the notes. I'm not going to draw that out. Okay. And if you don't have the, okay, I'll draw it out. You do have it, right? Yeah, it's on that paper. It's on your sheet of chemicals. Let's just start. I hate drawing these things. These things aren't easy to draw. All right, there it is. Beta-caryophyllene. Again, the most common sesquiterpene in all of essential oil chemistry. It's found in, like pinene and limonene, it's found in a lot of different things. If you could pull that out and let's look at it, the smell of it. Did you notice it's not as strong and overpowering as the monoterpenes were, right? Because it's not as volatile, It's a heavier molecule. So you get a different feel from it. Anything come to mind when you smell that? Cedar? It is a minor component of cedar. A lot of times you'll hear a perfumer characterize the odor of beta-caryophyllene as mushroom-like, sort of earthy. It's found in a good percentage in things like copaiba balsam, gurgeon balsam, which you don't have samples of. Where that would be things there would be a major component. It's a minor component in clove. You have a sample of clove oil there. I believe you have a sample of that. If you have the full kit, you already have access to that. It's down there in the last group, in the second to last of the last group. It's usually about 10% in clove oil. You're probably not going to pick it up because clove oil is mainly eugenol, which is a different, it's an oxygenated component, way different aroma. Huh?
Since you've got labeled eugenol, will it not be as strong as straight clove oil?
Would what?
It smells diluted.
What?
It smells like straight clove.
It's not.
Oh.
Which one? It's labeled. It's got written on there. It probably doesn't smell like clove oil if it's not clove oil. Let me smell your clove. That's excellent Madagascar clove oil. All these are pure essential oils, not diluted.
He's got agave in his.
Okay. So there you go. There's beta-caryophyllene. Cedarwood is loaded with sesquiterpenes, but if you're talking about like your standard cedarwood oil, like a Texas cedarwood, yeah, that would be more of and if we had it, I thought about putting that in this kit, but there's a sesquiterpene alcohol that's the characteristic odor of that, and that's cedrol. There's a cedrine, which is a sesquiterpene that the cedrol comes from. Yes, it's a sesquiterpene alcohol, yeah.
Do we even know the structure of beta-caryophyllene?
Yes, I want you to be able to reproduce those structures on the test. No. No, but I'm not going to ask you to redraw the structure, but if you see it, you should be able to recognize what it is. Especially know what class it is. But a matching? I don't know if I'll do that. Geez, come on. You guys are science majors. What are you talking about? I expect that from liberal arts majors. All right. All right, so still under terpenes. So we had monoterpenes, we had sesquiterpenes, and now we're going to talk about diterpenes. So if a monoterpene is 2 isoprene and a sesquiterpene is 3 isoprenes, guess how many a diterpene is?
7.
Yeah, 4 isoprene units. So therefore, the formula would be okay. Now, this is pushing the limit on what you can get by steam distillation on the size of a molecule that you can get. Now, you can get some oxygenated versions of diterpenes. Those are found in very small percentages. But you don't get much larger than these and their oxygenated derivatives. The largest molecule I've seen from a steam distillation process is probably either sclereol or insenso acetate. They're diterpene-derived oxygenated components. Basically, they're in the mid to like 330 to 350 range. I don't know if I've ever seen anything over 350, molecular weight 350 in an essential oil. Definitely not seen anything over 400. Okay, and the reason I'm pointing that out to you is because you'll see if you search for anything to do with frankincense oil right now on the internet, you will see there's a certain multi-level marketing company, which I won't name, that likes to claim that their frankincense oil, their steam distilled frankincense oil, has boswellic acid in it. Okay, boswellic acid. This is a side note. And I'm not going to go into the structure of boswellic acid, but it is basically an oxygenated triterpene, okay? And never seen a triterpene, just a hydrocarbon in an essential oil, and this is basically a diacid of a triterpene. So molecular weight is well up there, beyond 400. And it's not volatile. It's a solid at room temperature. It's not a volatile component. I would say it's physically impossible to steam distill boswellic acid at atmospheric pressure, which is where you do a steam distillation, without some other kind of manipulation. If their product actually does have that in there, which is, by the way, this is a cheap, readily available chemical from China. So if it is in there, you can imagine how it might make its way in there. But it's not a natural part of the steam distilled oil, okay? And I mean, I'm telling you, you can go on Google and just search for frankincense and boswellic acid. You'll find all kinds of claims of it, but it's, and I've conferred with other experts in the industry, and they all agree that you cannot distill that component. In fact, if you look at Wikipedia, the definition of boswellic acid in Wikipedia even says that it's not you can't steam distill it because of the claims made. But anyway, so the diterpenes are when they are found in essential oils, and I'm not even going to cover triterpenes because we never see them, but you could have a triterpene as a class of molecule. It would be, what would a triterpene be? How many isoprene units would a triterpene be? No. Mono is 1, you've got mono, which is 2, di is 4, so it'd be 6. Yeah. There's one in between there. That would be 5. But anyway, and we don't see those either. So I'm not going to cover anything beyond diterpenes. That's all you're going to be responsible for knowing anything about. They are pretty minor components of essential oils. There's some in cedar. There's some in minor components in, a couple of the wood oils. But one that I do want to point out is a structure called 16-carene. which looks like sorry about these skewed drawings. My hexagons aren't perfect. Yeah. And this last one is actually a 7-membered ring, not a 6-membered ring on this side. I didn't make a mistake. Okay. There's that. Now, if you count out the number of carbons and hydrogen, you should get C20H32. Wait a minute, sorry. Got to draw this little bridge. There. And that is a little bit misleading there. That should be that is a 6, 6, and 7-membered ring. All right, now, why am I drawing this? I had no idea that you could get, I've never seen a diterpene in an essential oil beyond maybe 1%, 1 or 2%, usually at a fraction of a percent. And a guy from Belgium contacted me who had distilled this Japanese cedar, which has the botanical name of Cryptomeria japonica. And the sample that he sent me when I analyzed it by GC, it had like 22% of this in this Cryptomeria, which I thought was noteworthy because I'd never seen a diterpene, which is a pretty heavy molecule, in a steam distilled essential oil at that kind of level. You just don't see that. So I am going to make some strips here and pass this around because this is a rare oil that probably less than 1,000 people in the whole world have ever even smelled before, and you're going to get a chance to smell it. I think it's a really nice oil. I'll just pass one to each row and just pass it down. It's not a real strong oil, but I think it's got a nice odor. It has potential for perfumery, and there's actually some articles written about it for some therapeutic benefits. Let's see here. What do you think? Oh, that's weird. Well, anyway, if I will post something on the Facebook page about this, but there was some work done with this oil on some skin disorders that it apparently had some really remarkable results, as well as a repellent for silverfish specifically. So, kind of interesting. Who knows what else? It's so new and so rare that, you know, who knows what other application it has.
Is that very expensive?
Yeah, it's fairly expensive. I'm thinking probably around $500 a kilo. Cheaper than oil. But, you know, it's, again, it's small production, very small production. I mean, there might be 5 kilos produced this year in the world. So, you know, if that production was ramped up and people started, growing trees for plantation, things like that. It could be cheaper. I'm sure of it. But just thought it was a noteworthy one to pause. So I put this one down because this is the largest. It's not the most common diterpene, but it is definitely the one that is present in the largest percentage of any essential oil. Thought about even publishing a paper on this because it's that unique. Is it in what?
Beechwood?
I've never seen an essential oil from beechwood. I don't know if you can get one. Okay. So that gets us through the terpenes that you're going to be responsible for knowing. Mono, sesqui, and diterpenes. So we've gotten through alkanes, alkenes, and the subclass of alkenes, and now we're going to talk about C, which would be the alkynes. So things to know about alkynes are their properties are similar to alkenes, except even more reactive still, because we have now the triple bond there that gives us more reactive site. It's linear geometry around the triple bond. So just like with a double bond, because of the bonding pattern here, you can't have free rotation. So single bond, you have free rotation. Then when you add this second bond, due to these pi orbitals, it fixes that. But now with the triple bond, you have p orbitals from the carbon forming another pi bond coming out of the plane now. So you've got bonding here and here to these lobes. That's what a triple bond looks like. So when you see this, you know there's no free rotation around that bond, but it doesn't matter because it's linear. So if you had, say, R group here and R prime over here, there's no worry about cis or trans because they're just in a straight, these are all in a straight line. So there's no cis-trans relationship either. IUPAC names always end in Y-N-E. And that's really all I'm at. You should know when you're talking, be able to recognize, and anyone who's had any basic organic is already going to know this, but you see Y-N-E, you know right away that's an alkyne. The simplest of all the alkynes would be just basically C triple bond to another C. Now we've got 3 bonds accounted for, so we can only have 1 left going to hydrogen. And for non-chemistry majors, what would you call that? Ethyne. Ethyne. But no one calls it ethyne. That's the formal IUPAC name. No one calls it ethyne. They call it acetylene. Okay. Which is used in torches and things of that nature. Yeah. We good on our volume level? Is our volume level good? Good. Okay. Okay. So honestly, alkynes in essential oils are almost non-existent. But I happen to have published a paper on that, so I'll post this up too. We did find one. I published this back in, when was this? In the 90s. I'm not sure when. It was in the Journal of Essential Oil Research. It was in an Artemisia dracunculus, which typically is a tarragon oil, but this is not a traditional tarragon. The traditional tarragon would smell like licorice, basically. This particular subspecies produced. There was no methyl chavicol, which is what gives you that licorice odor, but it had a very unusual alkyne that. Try to synthesize this in a laboratory, I would like to see, but it's strange. It had actually two of these things. It had this one, a conjugated alkyne attached to a benzene ring, and then it had this one. Just basically differ by an extra methyl group on this one. And this one is called 6-phenyl 2,4-hexadiene. Also, now, no one refers to it as that in essential oils. They call it capylene. Let me write that. Another name that I don't like, but it's what it's called. And why is that a bad name for that molecule? Ends in E-N-E instead of Y-N-E. Yeah. But since you almost never see alkynes in essential oil chemistry, it's not such a big deal. But just be aware of. Now, this particular molecule, these were found at like 11% for this one, which is called 5-phenyl-1,3-pentadiene, and then about 4 or 5% for this one. Never had seen an alkyne in an essential oil ever in my life until this oil, till we did this paper. And I'm sure there probably is another case of it out there somewhere, but it's just something you don't see. And I happen to have a sample of this oil. And you will literally be, before tonight, I would say probably 10 people in the world have smelled this oil. Not that it's a great smelling oil, but you're in an elite class of people after tonight. You think about that now. 7 billion people on Earth, and only now about 40 people have smelled it. So, or 30, let's say. Just pass it around. Just bring that one down this way. Pretty potent, huh? This was found to have some pretty significant insect repellent properties against a very... Huh? You smell those triple bonds? It's unlike any other oil I've ever smelled.
I think I got somebody stuck in my nose.
Does it have kind of citrusy?
Well, there's a lot of other stuff in here. See, I'm sure it has limonene, actually. It wasn't listed, but I can guarantee you there's a little bit of limonene in there. The major component was a monoterpene called terpinolene at 25%, followed by cisosamine, which we haven't covered the structures of those, but it's a very terpene oil for sure.
Where does it come from?
It comes from this plant. It's an Artemisia dracunculus subspecies. Unlike the traditional dracunculus, which is tarragon oil, which would smell completely different than this. Just thought it was noteworthy, and you might get a kick out of smelling weird stuff. But not really that useful for perfumery. Although it's somewhat Angelica-like. I don't know if you smelled Angelica seed oil. So who knows? It could maybe have a use, but it did have some significant insect repellent properties against a specific type of insect that was a problem for some kind of crop, and I can't remember what it was, but it's been a long time since I did this. In fact, that oil, see how dark it is? This is old. So that tells you right there, there's some I mean, it wasn't that dark originally. These alkynes are decomposing over time. I mean, they're going to. And we've refrigerated this even. Okay. So alkynes, again, not a whole lot you can talk about with these in terms of essential oils. Now when you get to fragrance chemistry, there might be some more molecules that would have examples that you would want to be concerned with, but naturally you just don't see a lot of them in essential oils. And probably because, when you're exposed to nature, you're going to have, when you have these highly reactive sites, they're going to find something to react with. All right, so that brings us to the final class of what. So let me again get where we're at here. We had the alkanes, we had alkenes, then under the alkenes we had the monoterpenes, or did we do, no, we did terpenes first as a broad category. Yeah, we did terpenes, and we did mono, sesqui, and di. And then we had the alkynes, now the final subclass under hydrocarbons are the aromatic hydrocarbons. Right? And when we say aromatic, we are not talking about how they smell. Ironically. By the way, speaking of words and meanings and things like that, I was just thinking about, your last name is Smells.
Smelts.
Oh, is it Smelts? It's pronounced Smelts? Okay. I didn't know how exactly, but it looks like it's Schmells. I was thinking, what an ideal name for a perfumer. Sarah Schmells. Okay, aromatic hydrocarbons. What does that mean? It means, well, mostly that we're talking about things that have an aromatic, what we call an aromatic ring, or a benzene ring, or a phenyl ring, whatever you want to call that. By the way, this is equivalent to saying this, okay? And you will see it written both ways. And the reason that is, this is benzene, is because when you have this cyclic conjugated planar structure that adheres to Huckel rule 4n+2 in the pi electrons, it gives it an extra stability over what a normal multiply double bound hydrocarbon would be. So in other words, when they figured out, hey, this is what the structure should be according to all the chemical tests we've done, but yet it's way less reactive than, say, that, which is also conjugated. Why? Why is that so less reactive? Well, it's because of this aromaticity, we call it, that gives it extra electronic stabilization. So they represent this as not only, you can imagine that this is not just this, but also this, which if we put that there, there, and there, and these bonds aren't moving like that. It's really that they're almost like 1.5 bonds all the way around. So it's equivalent. Each carbon atom here is equivalent. And each bond in between the carbons is equivalent. So that's why they use this to give you a better picture of that, what's going on. So if you've had organic chemistry, you're very familiar with all this, but just know that the aromatic hydrocarbon, when we call aromatic in chemistry, we're saying it's this kind of cyclic planar conjugated structure that has extra stability. Usually it's going to refer to this specifically in the molecule, this kind of group, this 6-membered phenyl group or benzyl group, but not always. And I'll get to some cases where that's not in a second, but an example of, say, the most common aromatic hydrocarbon would be this one. And this is called p-cymene. Okay, and you could also write it, with the circle here instead of the bonds if you want to. P-cymene. P-cymene is found in a lot of different things. Its formula, if you counted everything up properly, you would see that it is C10H14. A lot of times in literature, not scientific literature, but aromatherapy literature and things like that, people will classify, even in some fragrance chemistry, they'll refer to this as a terpene, as a monoterpene. Why is it not a monoterpene? It's not C10H16, right? It's 2 hydrogens short. Okay, that's resulting from this aromatic ring structure, which you don't usually have in the monoterpene. Well, you can never have in a monoterpene. If you have this, immediately you know it can't be a monoterpene if you see a phenyl ring in a structure. So p-cymene would be the most common example of an aromatic hydrocarbon in essential oil chemistry. It's found in oregano to a fairly large percentage. So that's why I gave you a sample of oregano. If you want to smell that and compare the two. It's also found in thyme oil, oregano oil. It's found in small percentages in a lot of oils, but it's a high percentage in those two. To me, what's your impression of it when you smell the p-cymene, first of all? If you're having trouble with those caps, the best way to get those off is don't pull directly away from them, but just kind of bend them. Twist a little bit, then bend. It could be that some of those cough drops have thyme in them. It reminds me a little bit of thyme because it isn't thyme oil, but some people characterize the odor of paracymene as gasoline-like. because it is very hydrocarbon-y smelling. But again, it's found in a lot of things at small percentages, and then thyme and oregano at high percentage. Now, I wanted to talk about an example of a commonly mischaracterized molecule that also falls under this category, and that is this. That. This is called Chamazulene. Get my other marker here. The formula is C14H16. This is often referred to as a sesquiterpene. But, as we see, it is not a sesquiterpene. Because the sesquiterpene must be H24. C15H24. So it's one carbon short. Obviously, you can't be a sesquiterpene without 15 carbons. The interesting thing about this molecule, which is found in things like German chamomile oil, which is also called blue chamomile oil, it's found in a blue tansy oil, and it's basically in every oil that's blue, called a blue oil because it actually is a blue color. So this molecule is responsible for that blue color in these blue essential oils. And I have an example here of the blue tansy. That's right, that's where the azul comes from. And this molecule has been attributed to having anti-inflammatory properties in essential oils. So it's like blue chamomile would be, and see, it's so intensely blue that this almost looks black, like ink. But you can clearly see on a strip, you know, it's dark blue. This is the blue tansy. I think I got an extra one here, so maybe I'll have one. Here, I'll start this one down at this end. I think it's a pleasant odor. The Chamazulene actually does not have any odor at all. It's an odorless component, but because of this, why is this aromatic, first of all? Chem majors.
Flat, cyclic, satisfies the 4N plus 2 rule.
How? What's the...
There's 14 carbons, so if N equals 3, 4N plus 2 is 14.
Well, there's 14 carbons.
Okay, wait, yeah, you're right. 1, 2, 3, 4, 5, 6. Okay.
How many pi electrons? There's 10 pi electrons, that's right. So 10 pi electrons, and we have to satisfy 4n plus 2 equals 10. What would n have to be there? Obviously, it would be 2. So yes, it does satisfy Hooke's rule. It's planar, because all these are trigonal planar geometry sp2 hybridized carbons. It's cyclic, and it's conjugated. All is satisfied. And indeed, we do see additional stability, electronic stability, because as a result of this arrangement. So you could actually, if you wanted to, you could represent this molecule like this. Okay, where it's equal sharing, pretty much. Not exactly equal, because these, you got a little bit difference of environments here, but roughly equal. And it's Chamazulene. There are some other azulenes. Guaiazulene is another one. It's just basically a different substituted variety of this, but less common. Chamazulene is by far your most common non-phenyl-related aromatic molecule. And ironically, it's odorless. It's aromatic, but it's odorless. It's a solid blue crystal, a very valuable one at that. It used to be produced by a company out of Hungary, but I don't even know if you can get it anymore. It used to be like $1,000 a kilo for that stuff. But it's a desired, basically your quality of things like blue or German chamomile, blue tansy, any blue oil, its quality is going to be measured upon how much of this is in there. It's a very desirable molecule. Okay. Well, that brings us to the end of the hydrocarbons. Is there any questions over any of this? None? Really?
What is the structure of blue oil? Well, the main component.
Well, there isn't one like main component. It's like hundreds of the same. It's like spread out all these components that are the same. I know there's things like Elamol in there and a lot of sesquiterpene alcohols and sesquiterpenes, but I'm sure there is a main component, but it's not like it's drastically major, like 70 or 80.
Figure out the enzyme, synthesize one thing, and be a billionaire.
Oh, no, it's so complex. Now, if you want to do one thing, I'll tell you what, if you want to figure out how to make a lot of money in this industry, if you can figure out how to make santalol, which is in sandalwood, main component of sandalwood, make that synthetically at an affordable price, you'd be a millionaire. If you could figure out how to make lavendulyl acetate, you'd probably do all right. If you could figure out how to make nepentolactone, which is the most potent natural mosquito repellent molecule out there, you'd be doing well as well. Those are 3 right off the top of my head. There's others, but those.
The one that's in
Catnip oil, right. Yes. Mm-hmm.
Is there new essential oils being discovered all the time, or is it?
There's always something out there that somebody's doing that no one else has done, and whether or not you hear about it or not, I mean, I have access to a lot of more than what most people do because when people do something like that, they usually contact me and ask me to analyze it or whatnot. So I keep an ear to the ground on that kind of stuff.
So most of the stuff like around here, the botanicals and things, people have steam distilled and seeing what types of oils they can get out of.
Everything around here probably somewhere has done it, but that doesn't mean that the oil that would be produced from a plant here wouldn't be different than, say, somewhere in Bulgaria. Because the climate and the area, the altitude, all that affects the quality of oil that comes out of the plant. I mean, you can literally have the same exact species grown in 2 different locations have drastically different chemistry. Drastically different. You could even have the same plant growing on the shady side of a hill and on the sunny side and get different oil. That wouldn't be drastic, but you could get different oil. Anything else? Okay, well, next week we'll hit the alcohols, and so be thinking of be thinking of turning off your cell phones before you come to class, and be thinking about questions from this week as you're going through the notes. I will post the notes again on the site from today, as well as the video of today's class. And if there's anything from today that you had a question about, we'll cover that first in the first half hour before we move on to anything else. So those of you who have to be late, if we do continue at 6 o'clock, you won't miss it. Actually, if you have to miss the whole class, you still could get the video. But there's people that would like to bump the class up to 6:30, which I don't have a problem with. But I don't want to do that if someone does have a problem with it. So what I'd like to do right now is just take a piece of paper, and we're going to have a vote on whether we'd like to move the class to 6:30 or not. And you can just write yes, meaning yes, let's move it to 6:30, or no, keep it the same at 6 o'clock. Mm-hmm.
Would that be 6:30 to 9:30?
It'd be 6:30 to 9:30 formally, but a lot of times we might get out early. The reason I don't want to do it unless everyone's on board, because people paid for this class based upon it being at 6 o'clock. And if you've paid for the class because that's the way it was advertised, and we change it, it's not really fair unless everyone is okay with it. So when you get that, we're good, yeah.